Good morning everyone, I am Hatim Kanchwala and I will be presenting on EDSAC Museum on FPGA, which was my Google Summer of Code project with Fuzzy Foundation. So first on agenda, I would like to talk to you about how the project came to be. A colleague of mine in 2015 was working on a C, C++ simulator for the Witch, the Harwell Witch, Wolverhampton instrument for teaching computation from Harwell. So this is the Decatron computer, which is fully functional in the TNMOC, and it's the oldest fully operational computer, and this is where I wanted to work with retro computers, and it got me interested in this field. And so I talked to them, and I wanted to do a HDL implementation of the Witch, but they did not want to do it in Verilog. So fast forward to 2017, FOSSEE had a very nice project to replicate the EDSAC on an FPGA. So this year is the 60th anniversary of BCS, whose founder is Maurice Wilkes, who built the EDSAC in 1949. So under the mentorship of Jeremy Bennett and Stefan Valentowitz, I did this project this summer, and a great deal of help from Bill Purvis, who is in the audience. He is the original logic designer for EDSAC, and his work made it possible for the EDSAC to be reconstructed. So the project's main aim was to reimagine the EDSAC for a modern generation of computer engineers and hobbyists. If they could get the EDSAC on their boards and their hostels or in their dorm rooms, or so they could try out and learn about this machine. So let's talk about the EDSAC, the actual machine now. EDSAC is the electronic delay storage automatic calculator, and it was Maurice Wilkes was inspired from ENIAC and EDVAC before it, and EDVAC was in the US, and it also has delay lines, which was the main source of inspiration for Maurice Wilkes to build his EDSAC. And if you look at the diagrams of these machines, they are also arranged very similarly. So EDSAC ran at a clock of 500 kilohertz, and it had 18 instructions, there's a typo there. Arithmetic instructions, logical instructions. There was just one logical instruction, the AND operation, which was called collation. We'll look about it in a few slides. And then there are branch and shift and round off operations. The round off operations are is something Maurice was very proud of, and we'll look at how it is important here. A few terms before we dig deeper into the EDSAC. So the EDSAC has 2 microseconds of clock. The width of a clock pulse is 2 microseconds, and that's what they call a pulse interval, and they also call it a bit because every clock pulse they had 1 bit. 16 pulse intervals made 1 minor cycle, and that's of 36 bits, 72 microseconds. 1 major cycle was a duration of 1.15 milliseconds, which is 16 minor cycles. Please keep these terms in mind, we'll be using these. So the number representation in EDSAC was in binary form, but it had a real number representation. So numbers began from -1 up to 1, and you had the first decimal digit and then followed by the decimal point, and then there were 2 kinds of data, the 2 kinds of numbers. One was a long number and one was a short number. The long number is of 36 bits, of which only 35 bits are usable, and the short number is of 18 bits, of which only 17 is usable. So the first bit in each number is unusable because of circuit setup times. And yeah, 2's complement is used for negative numbers. The input for numbers and orders are instructions. The input comes from a punch tape reader, and the output is to a teleprinter. And it was when it was orders and numbers were punched into the tape, they were in the decimal notation, and the conversion to binary was handled by the machine when the input order was being executed. So we've covered this already. And the Mercury, let's talk a bit more about Mercury delay lines. The Mercury delay lines were around, they used the acoustic property of Mercury, where they had transducers at 2 ends of it, and a pulse was fed inside, was modulated, and through it traveled through the mercury delay line and arrived at the other end 1.15 milliseconds later. So you had 16 long words in continuous recirculation, and since mercury was a hazardous material, it had to be maintained. In the current replica that is being brought up in TNMOC, they are using nickel delay lines instead of the mercury delay lines. The memory capacity of EDSAC was 512 long words, which is roughly 2 kilobytes, and it was spread across 32 memory tanks, which were spread across 4 racks, and this was later expanded to 1024 long words. So over the 10 years of operation of EDSAC, we had several iterations of EDSAC, which not all of them are documented well. Now we'll look at some of the very basic units which build up all the modules of EDSAC and then the subsystems. The most fundamental unit is a delay line, which we've just spoken about, and followed by that is the flip-flops. These are in quotations because these are asynchronous flip-flops. They are not flip-flops that you expect them to be. They are resettable monostables. They have a set and a reset signal, and there's one race condition possible if you have the set and the reset signals the positive edge at the same time, then you don't know what state you might end up in, and these are not clocked. That's why it's in inverted commas. The AND gates were simply referred to as gates in the original report, and they had 2 input, 3 input, 4 input, 5 input AND gates, and OR gates were just referred to as adding diodes. So this is any general module of EDSAC is built up of delay lines, gates, adding diodes, or flip-flops. This is how the Verilog in the code is modeled. We first built the delay lines since the delay line in the original EDSAC was an analog device, so we had to replicate this, and my idea of replicating the delay lines was to use a circular shift register. For flip-flops, we did not have a clock, and it was pretty straightforward, but we need to avoid the race conditions, so every reset input is delayed by a few seconds. Then gates and OR gates are pretty straightforward. So at the top level of the EDSAC, we can break it down into 5 units. We have computer. They call it the computer, but it is now the ALU, control section, IO, memory, and then pulse generation and clock and power supplies. The clock is actually an interesting way. They generate the clock pulse in a very interesting way. I was just having a conversation with Bill, and they had sine waves which they amplified, and then they simply they passed it through the valve circuits, and that just cut off the top of the sine wave. So you had roughly square waves. If you look at it in the current terms, you could imagine it to be an op amp where it's just being cut off at plus minus 12 volts. So that's how they generated the square clock pulses. The computer has the accumulator, which is 72-bit wide, so that it accommodates the result of a multiplication. The multiplication operation was the most significant feature of EDSAC. It has 2 registers, the multiplicand tank and the multiplier tank, each of 36-bit wide, and you have an adder there. You also have a dedicated complementing unit that it's responsible for the 2's complement that EDSAC follows, and you also have a distribution unit followed by a collation unit. The collation is simply AND, and this was the only logical function the EDSAC had at that time. Throughout this unit, there were effectively 2 minor cycle delay when a number arrived, and when the number left the computer, there were 2 minor cycle delays. So one minor cycle puts the entire operation back in phase, but if you have few pulse intervals, plus minus a few pulse intervals, and then you start to have timing issues. Timing issues were very frequent in the simulations that I ran, so that's something to take note of. Now moving on to the control section, there were 2 stages of control in the machine. When the first the stage 1 was when the order tank was loaded from the sequence control tank. The sequence control tank had the instruction from where to fetch the the order from the memory. The sequence control tank was then passed on to the coincidence unit. Coincidence unit is responsible for finding the exact number within the rack and then the number within the mercury delay line. So there were 16 numbers in circulation, and you had to find, let's say you had to find the 10th number. So coincidence unit was responsible for opening the gates and allowing the 10th number to be put on the output bus. So once the order was loaded, it set up a few, the order flashing unit set up a few flip-flops, which the flip-flops were mainly used because they wanted to have bits to be held in that state for around a few milliseconds. The order flashing unit is where the 5 bits of the order opcode were held for some time, which then propagated to the order decoder. The order decoder is, so the order decoder has 2 stages. The first stage uses the 2 most significant bits, followed by the 3 most significant bits, which are used in the second stage of order decoding. At the end of this stage, you have the opcodes which need to be, the opcode which needs to be executed. This passes on to the order coder. The order coder is responsible for setting up all the control signals, which then propagate to the computer control unit, and to other timing and control units in other subsystems. And once the order is loaded and you have the stage 1 is completed, that's when the stage 1 starts. The stage 1 execution starts by setting up the if you need a memory access, then you have to get from the memory the data into the accumulator, and that's when the coincidence unit and the tank number decoding units come back into picture. I think you'll remember that I was talking about how numbers flow into the computer. They flow in through the multiplication units and they flow out through the accumulator shifting unit. That's how the delay is propagated. Yeah. So this is the control unit, the entire control unit. It's the most complex unit, and there are a few more units which are auxiliary to operation. The first one is the transfer unit. Since the EDSAC had 2 kinds of data, one was the long number and one was the short number, and it also had a fixed decimal point, the short numbers needed to be aligned with the long numbers, and that's where the transfer unit comes into picture. It's just so that the decimal number aligns and the adding operations or the multiplication operations produce the right result. So the result flows from the accumulator into the memory via the accumulator shifting units, and from the memory into the multiplicand unit. The multiplier register is separate. You will note that there are 2 multiplication registers here, but we could have just done with one of them. So at the top level, we have completed the control section and the computer, and the I/O has a teleprinter and a punch tape reader, which is pretty straightforward, and the modern replica of these, Dan, Peter and Mary will be presenting just after me. Apart from the teleprinter and the punch tape reader, at the EDSAC also had CRT screens which display the contents of the accumulator, the multiplicand tank, the multiplier tank, the order tank and the sequence control tank. These were displayed on a CRT screen with a dot showing 1 and the absence of a dot showing a 0. Maurice Wilkes was pretty proud of the CRT screens because at that time not a lot of computers had that. The Decatron has a very interesting arrangement. The Decatron operates on, instead of binary, it operates on decimal logic, because the Decatron is actually a 10-stage, you can see it counting. In the initial orders were also a pretty interesting part of EDSAC. Initial orders are something that it's kind of like bootstrapping, which we have now. So for orders to be in the memory from the punch tape reader, you need to issue an opcode, which means that the instruction has to already be in the memory. So that is why the initial orders come in, because they load the orders from the punch tape. You had a set of around 40 to 50 toggle switches which you need to set. There were 2 versions of the initial orders. Once you set these and started the operation, the relays would come into picture and the initial orders would transfer into the memory. Those would load the punch tape reader, and the orders and numbers from the punch tape reader were then read into the memory. So as I was saying, there were 32 memory tanks spread across 4 racks. Within the racks, there were 2 sections, one at the top and one at the bottom, 4 tanks at the top and 4 at the bottom. Later in this, in its operation, it was upgraded to 1024 long words. So I'd like to talk about the current status of work. We have, at this URL, we have the repository up. Almost all modules are noted down. I mean, all modules are prepared. The goal was to be very faithful to the original replica, so we did not choose to, we chose to be very faithful to the original designs and the original architecture the report was talking about, but the report was published before the machine was actually built, so we are very short on documentation here. And that's why there were quite a lot of issues in the implementation of this project. We had significant timing issues where the delays were propagating and we did not know where these delays were being introduced. So when the orders transfer from one unit to the other, there were issues with alignment. Now, once this is complete, I'd also like to work on 2 very interesting ideas that I had from the start. The entire FPGA replica of EDSAC is on the MyStorm board, and the MyStorm board is, thanks to Ken and Alan, it's a very low cost educational board, it's an open source board. So the EDSAC is on the FPGA, but the peripherals of EDSAC are also very interesting, which are not being replicated with this project. I've kept it as further work because the peripherals should also have a modern replica of sorts, and I like to call it the IO flavors. It's quite simple, as in the FPGA is something accessible to everybody, and if people are interested, they can port it to Xilinx boards or Altera boards or any other boards that they have. But to get the peripherals working, I do not want to stick to just one of them. You could have if you have an Arduino or if you have a Raspberry Pi with you, you can hook up your Raspberry Pi or an Arduino or a Teensy to build your own peripheral. Like I had an idea of building a Raspberry Pi connected to the FPGA board. The Raspberry Pi sends in the initial orders along with the entire instruction, and you're able to view the contents of the memory bank and the registers on your screen on the Raspberry Pi. People could do it with a Teensy, or they could simply use breakout boards. This is one area that I would like to explore broadly. Then there is of course the assembler. In ChipHack we had, I think we had Dan who built a very basic assembler, and that's a link I can share. And yes, if you have any more ideas to extend this, we are available at this link. Please send pull requests, please raise issues, and if you would like to get in touch, that's great. I'd like to thank FOSSEE Foundation and Ambicosm for sponsoring this presentation, and they've sponsored my trip, so that has made this presentation possible. I'd also like to thank my mentors Jeremy and Stefan. They've been a great help, and Jeremy has been very encouraging throughout the project. Huge thanks to Bill Purvis, whose logic design work helped make this project, and Professor Martin Campbell Kelly, who is the de facto authority on EDSAC, and Ken and Alan for the MyStorm board. So I guess that's it. Thank you. Any questions?
So did you work as base for the project? Did you work from written documentation and logic diagrams?
Oh yes. So there was the original report by Maurice, and there was the reconstructed logic from Bill, and so these were the basis of all of those. And I had a couple of issues especially with initial orders. So I corresponded with Bill and Professor Martin Campbell Kelly. So they gave me a few more documents to look over, and we had the initial orders, the original set, which there were the second version of initial orders which Wheeler wrote. I got those from Bill, and the first is also available. There was a great help from Martin's simulator as well.
Thank you.
Slightly off-topic question: is that a working QR code?
No, this is This is something called a square Kufic calligraphy. This is my name written in Arabic in 4 orientations.
Fantastic.
Yeah.
Thank you. Did you have to learn how to read the circuit diagrams with the original valves and work out the different types of valves and what they did?
I did look at it and then I shut it very quickly.
Good choice.
Because Bill's logic reconstruction was very helpful. He made it down into gates, and he also has a simulation, and Professor Martin's simulation was very helpful. So I did not have to resort to looking at Valve data sheets, thankfully.
Thank you.
Hatim, great work.
Thank you.
Very challenging to look at the architecture of such an early machine and try and get a modern day sense of it. I suppose that when you program in Verilog, it's very easy to be abstracted so many layers away from the actual machine, and EDSAC only had 18 instructions and only about 14 of those were useful. And in Verilog it would be very simple just to have 14 lines of code saying what the next output of the ALU is going to be, but you've kind of gone to a faithful reproduction of the logic as it was originally designed. Yeah, so well done. Yeah,
Thank you.
Just a general question. What was your motivation to go into such a project as a very young guy?
I just like looking at I don't know how I put it. It's kind of like philosophical thing with me, because currently where we are in computer architecture or in whatever phase we are, it gives us a lot of context to look at how it evolved throughout the history. This was a computer. They call it a computer, but it was more like a glorified calculator with quite a lot of focus on multiplication. This was the first, arguably the first stored program computer. Before it, it was a Manchester Baby. People say that the Manchester Baby was the first stored program computer, and these were the roots of the von Neumann architecture. So it gives me sense and context to the knowledge I'm receiving in my courses, how it evolved and why it evolved that way. That was the motivation.
For your next project, are you considering the Apollo guidance computer?
If it does not have Wolf circuits,
Sorry, say
if it does not have Wolf circuits,
Yeah, well, you can imagine it's got all gates, not all safe gates.
sure.
Yes, we ran out of questions. Thank you. A huge round of
Thank you.
applause.